There was a new the LIGO gravitational detector just it was announced. They just detected a neutron star merger, and since there's now a functional detector in Italy that could triangulate the direction to the source, and had a telescope on it within 15 minutes, an optical telescope, and watched the optical event in synchrony with the gravitational event. It's very cool. Homework 4. Got a couple of questions last night at 8 o'clock, which is just about my bedtime. But anybody have any questions about question 1? Describe in detail why there is a diode across the motor. Is that clear? The snubber diode, it cuts out the back EMF from the inductor. It keeps the field effect transistor from turning back into sand again. So the second question, though, explain the physics in the MATLAB code. Now, I'm going to go over the MATLAB code in a little while, but I think I was wrong. I think there was a problem with the physics. And a couple of people pointed it out to me. What's the consensus? Should there have been a cosine term in the torque? Yes or no? Yes? No? Don't give a damn. Right? All right. So, probably there shouldn't have been. But any questions about the MATLAB code? Do you want to go through that right now? Yes? Was that did I see a handshake, a head shake? Yes? Okay. There's two versions. Let's use the second one that's in ADC units. And so there's a whole bunch of initial conditions and a whole bunch of guesses about parameters. And the part that you're going to end up designing for this exercise are the control constants, a proportional term, a differential term, and an integral term, which we'll talk about later in the lecture. The motor low pass was my guess about the speed at which the motor accommodates a new voltage, and so it's part of the physics, which you wouldn't modify. But the first part of the code describes the control algorithm in terms of a PID controller. And I thought I'd give you this because I think there's enough to do to get the C working that it's still significantly hard. Because converting from MATLAB means devectorizing, scalarizing everything, and making it real-time rather than batch-oriented like MATLAB is. So there's some sort of voltage that's going to be calculated as an output, and I'll talk more in detail about that after I go through the algorithm. But you're going to detect the actual angle. You know the desired angle, plus 30 degrees. You're going to measure the actual angle. You're going to calculate an error, and then you're going to do things with that error. You're going to say, I want a voltage which is proportional to the error. I want a voltage which is proportional to the first derivative of the error. I want another voltage which is proportional to the integral of the area, and add those all together. We're going to go through this in some detail, but this is just the warm-up. So these are the terms that calculate the various proportional, differential, and integral terms. And then there's a couple of bounds we need to put. PWM can't make a negative number, so we're bounding the output at 0 on the bottom, or another way of saying that is we can't run the motor backwards. We only have a single, we're not running an H bridge here, we're only running a single transistor, so we can't run the motor backwards. And secondly, if the number calculated for the output gets greater than the maximum that the PWM can sustain, we better not wrap, because that'll produce a lower RPM, not a higher RPM. So we're going to bound the upper level to the maximum level of the PWM, and by saying 39,999, what I'm saying is that the period of the pulse width modulator is going to be 40,000, or in other words, 1 kilohertz. 40 megahertz divided by 40,000, 1 kilohertz. So this assumes a 1 kilohertz PWM. It's fast enough. And if you do that, if you change the rate, say, I want to make it go 2 kilohertz, then you're going to have to change this down to 20,000. Because you don't want to overflow the PWM. You want it to saturate on the bottom at 0. You want the PWM to saturate on the bottom at 0, be linear up to some max, and then saturate at the top and not wrap. The physics piece of this is a bunch of head-scratching and educated guesses. The motor, the relationship between a step in the motor voltage, if the voltage gets stepped, how does the speed of a motor change? Turns out it's more or less a first-order system. It more or less goes up exponentially. And so I modeled the motor, the response of the motor to a step in voltage as a single pole low pass filter, a simple RC low pass filter, digital low pass filter. Scaled the thrust produced by the motor to the RPM squared times some constant I sort of pulled out of the air. And RPM squared is reasonable. It doesn't actually quite go, it quite goes a little bit faster than that at high RPM. And then when you start getting towards Mach 1, it doesn't work anymore at all. But we're not anywhere near that, I'm happy to say. So the lift torque is the thrust times L, and that cosine probably shouldn't be there. But since the maximum and minimum angle are plus minus 30 degrees, what's the cosine of 30 degrees? You don't remember that? 0.866. So even if this isn't here, it's only 10% off. For simulation, that's good enough. And in fact, leaving that out doesn't really change the value of change the simulation very much, but it probably shouldn't be there. Beam torque is given by gravity times cosine, because gravity is always pulling straight down. The torque from the motor is always at right angles to the beam, but the torque from gravity is not at right angles, and so we do have to pull in a cosine there. So this is the gravitational torque here, and so that is mass times g times L times the cosine of the angle. And then we do some sort of weird scaling. Times 256? 265? What the? So I tried to convert the units here from radians to ADC units. Remember, you're going to be measuring the angle in terms of the analog digital converter. And rather than change the analog digital converter to radians and then calculate radians, why not just calculate in ADC units? But to do that, you have to scale up by 265. I'll show you where that number comes from in a little while. So we subtract the torques because we're interested in the angular acceleration. We scale by the moment of inertia, and then do a numerical integration, Euler integration of the angular acceleration to velocity, and then velocity to angle. And so really what we're saying is that there's two torques. We're going to subtract them. We're going to get the angular acceleration, integrate it to position, and what we want to control is the position. But is there any question about the physics? Yes.
For the lift torque, what's the direction of the force?
Right, in the direction of the propeller.
Oh, so it goes up or it goes up, right?
It is pushing downwards.
So it's the same direction with the correct.
But so it's blowing air downwards, and so it's accelerating upwards. What else? What MCU hardware is used by protothreads? How would you find that out? How did you find it out for this question? Ask a TA. How did you find it out? Did you read the documentation? How'd you find out? Read the documentation? Yeah, it works. And what is used by protothreads? Timer 5, for sure. Is the UART used? If you turn it on. Is VREF used? If you turn it on. Otherwise, no other hardware is used. So, can you use timer 2 for your own code? Obviously you can. You used it in labs 2, 3, labs 2 and 3, 1, 2, and 3. And then 4 caused some discussion. How would you measure the CPU load caused by the motor control ISR running at 1,000 hertz? Who came up with a good answer for that? Nobody? Anybody want to answer? Yeah.
Since the timer rolls over as soon as it hits triggers the ISR, you can read the timer at the end of your ISR to know how many cycles it took to get to the end. Since the ISR happens 1,000 times in a second, times 1,000 divided by clock frequency.
That's approximately right. If you put a timer measure at the end of the interrupt service routine, you get the length of execution of the interrupt service routine, except for the time it takes to exit the interrupt service routine. But yes, and then you know the number of cycles it took, you know the total number of cycles per second, you subtract it from the total cycles available.
Could you just time it using a different timer? Just like retimer, I don't know, not the one that's in the ISR?
Oh, sure.
Before the ISR, inside the ISR, outside the ISR, just calculate the whole in, during, and out.
You can't read it outside the ISR because you don't know when the ISR happened outside. And since it's asynchronous with respect to the main program code, you can only read the timer inside the interrupt service routine to get interrupt service routine related things. Now, what you could do, though, which would work, is turn on a bit when you enter the interrupt service routine, turn it off when you exit, and look at it on the oscilloscope. Take the ratio of this height over the total distance, that gives you the load on the CPU. Except for the time it takes to get in and out of this interrupt service routine. So another way to do it is you write in your scheduler, you're going through these threads very, very quickly. Let's say you comment out everything in every thread, so that the scheduler is just sitting there saying, are you ready to execute? Nope. Are you ready to execute? Nope. Are you ready to execute? It's going through that loop millions of times a second. So in main, now in your main that is absolutely a null main, you toggle a bit. You toggle a bit just as fast as you can. And it turns out when you do that, it's about 8 megahertz or so. I've tried this. You toggle a bit. When the interrupt fires, the bit step stops toggling and then starts toggling again when you're back in main. So if you go from here to here, then you get a pretty good estimate of the total time that the interrupt service routine has taken over the CPU, including exit time and entry time. It's kind of like the shadow left when main can't execute. So any of these methods will work. The easiest way to do it was to look at the code I put up and talked about in class for Lab 2. And that was timing test source code for an interrupt service routine. So to get the time it takes to get into the interrupt service routine, you read the enter time, then you go through the interrupt service routine, read it again at the end of the interrupt service routine. This is the time for entrance plus the total execution time of the interrupt service routine. The time for exiting is the same as the time for entrance, so we once again add the entrance time to this, and we get the total time for the interrupt service routine. So really all you had to do to answer this question was to go back and remember that we did it in Lab 2. So any other questions on homework 4? This is really an exercise in getting you to read the documentation, like all the homeworks are. Any other questions on on homework 4? All right, let's go back and talk more about the lab itself. How many people have built up the hardware, the beam? Half? Something like that? Yeah, maybe a third. Were there any quirks that you would like to talk about that I should change in the directions? I changed one thing today that I think makes it easier. And it's not here yet, so let me reload this. Now it's here. Hot glue the motor to the beam before you put the knob on. That way you can lay them both flat on the tabletop. It's easier to hot glue. So I changed that. I changed the order of the knob and the motor being glued on. But from what I've seen, it's straightforward if slightly time consuming. So the goal here is to produce a control system that is going to allow this very non-ideal pendulum to assume a certain angle depending upon what you want. And the way this is usually written is to say we want an input which is something like, we're going to just call it the desired angle, and we're going to subtract from that the actual angle. So we're going to then calculate some error in the angle. Then we're going to have some calculation which says, how do we want to set a voltage? We're just going to call this the PID algorithm for now. And out of here is going to come a voltage specification. It's actually going to be a PWM specification, but it's proportional to voltage. So this is going to be a PWM specification. Then we need a model for the motor itself, which translates a voltage into a speed. We'll just call it omega dot, angular speed. And then we need a function which is going to model the pendulum dynamics. The pendulum, which includes the motor as the main mass. Then we're going to feed that back through a sensor. And the sensor is going to actually give us the angle omega as measured. And that's what gets fed back to produce the error. And I'm going to do this partly qualitatively, partly quantitatively, because I don't want to spend a lot of time on the control theory. But we're going to need some model for the motor, mathematical model for the motor. We need some mathematical model for the pendulum. The sensor is easy because it's almost a pure scalar translation from angle to a voltage through the potentiometer. And what we want what we really want is that if we have time here and angle here, that if we ask for this set of steps of angle, so this is the desired angle, desired by the user, that what we should get is something at the actual output that mirrors that rather closely. Without too much oscillation, which I'm showing here. I'm showing some oscillation here, without too much overshoot or undershoot. And ideally we'd get an exact copy, but we can't ever get an exact copy because everything has mass and a finite response speed. So we want to get as close to a copy of this square wave as we can, consistent with motor power and computational speed and the physical setup that we have. So this is the model we need to generate, and then based upon this model optimize the PID controller to get a result that is as close to the waveform as possible. And because every step of writing this code and making it run is going to depend upon you knowing what the motor response is and what the actual angle is, the first thing you're going to do in the interrupt service routine is get the plotting functions working for angle. So that when you move this thing by hand, when you move that beam by hand, you can watch the angle change on the oscilloscope. When you change the voltage on the motor, you can see the motor parameter change. Once you've got that running, then you can feasibly debug the system. So what's often done, and what we'll do here, is we'll really decompose this, sort of Fourier decompose this, and we solve it for one sine wave. Since it's a linear system, since all these operators are going to be linear operators, then if we solve it for one sine wave, we've solved it for any possible input, because superposition holds. And we can always Fourier analyze the input, pass it through the system, re-Fourier synthesize, get the result out. So we're only going to solve it for one frequency. And if we convert these all to frequency responses, then concatenating operators one after the other is equivalent to multiplying their frequency response. And we can write the output here. This is the output. We can write the output as a function of f. And now this is going to be a vector because it's going to have phase and magnitude. It's a phasor. It's going to have phase and magnitude is equal to some control function, the PID function of f, times the motor function of f, times the, what did I call it, the pendulum, the device function of f times the error. And again, these are all phase magnitude quantities. And we can rewrite this as c times m times d times the error is the desired angle minus the output. So the output then is the desired angle times, oh dear, c times m times d over 1 plus c times m times d. Well, if the magnitude, this has got some complicated phase and magnitude, if the magnitude of the product of c times m times d becomes big, becomes much greater than 1, if the magnitude of that, no matter what it is, some horrible complex function, no matter what it is, if the magnitude becomes large, if this becomes large, I should say if CMD becomes large, then the output is approximately equal to the desired. That says that if we turn up the gain enough, we make the PID big enough, some gigantic constant, the output will be arbitrarily close to the desired, independent of anything else, independent of the motor dynamics, independent of the details of the pendulum dynamics. But there's a catch. And that is that as you turn up the gain more and more to make this system more and more accurate, then phase shift at high frequency starts to hurt you. And to see why, then we have to do a little bit more detailed modeling. Any questions at this point? So, let's make a model of the motor. Actually, it turns out, let me abstract away the motor for a moment and say the motor acts like a second order system. The motor looks like a resistor, an inductor, a back EMF, all attached. So if you attach this to an external voltage source, the motor itself looks like a resistor, series resistor, a series inductor, and a back EMF, because every DC motor is also a generator. And as you spin this thing up, the back EMF increases, the current drops. If you solve this, you get a second order system. Let me just abstract it away and say, if we look at log frequency versus log amplitude, or let me put it better than that, as the log of the omega over the applied voltage, so the speed of the motor divided by the applied voltage, we get a curve that looks like this out to some frequency, and then it drops off just like a low-pass filter. And except that the asymptotic slope here, the asymptotic slope is -2 on a log-log plot, so it looks like a two-pole filter. There's some time constant we'll call tau motor. And the reason I'm going to abstract this away at this point is that the motor is really fast to change speeds. So this is a rather high frequency. Tau m is rather small, so 1 over tau m, I should say this is 1 over tau m. 1 over tau m is a relatively large frequency, the cutoff frequency of the motor. And because the pendulum is much slower than the motor, we can treat the motor as being arbitrarily fast. In other words, we don't care about the time constant of it. It just is instantaneous. Turns on, turns off. You put a square wave pulse into it. From the standpoint of the pendulum, the motor rises instantaneously. So while this matters for the response of the system, it doesn't matter very much because it's so much faster. The time constants are all dominated by the low-pass characteristic of the pendulum and the resonance of the pendulum itself. So clear why I'm abstracting this away. You probably all got the pendulum equation beaten into you at some point or another in introductory dynamics or physics or someplace, right? So if we do the Bode plot of the pendulum, if we do a Bode plot, wonder if it's legal in California. So we have log F versus log A for a pendulum now. So this is the pendulum. We find that there's a more or less sharp increase in amplitude at a given frequency of input corresponding to the resonance of the pendulum, which is the free frequency. If you take this pendulum and you hit it, it rocks back and forth. That gives you the natural frequency of the pendulum. How are you going to get that? Well, the first thing you're going to do is to get the DAC showing you the angle of the pendulum. You let it dangle, you hit it, you record the waveform on the oscilloscope, you measure the period of the waveform. That gives you the natural frequency. So you're going to be able to get this natural frequency, and you can also get the width of this, because the width of this is related to the damping coefficient, but you're probably not going to use that directly. You'll probably just use the damping coefficient, which is given by how many cycles, more or less, does the system undergo before it stops. For your pendulum, the friction is going to be dominated by two physical effects. The first physical effect is that the potentiometer has internal friction, and that will slow down the pendulum. The second is, unless you're very, very careful about the way you route the wires coming off the pendulum, those will add to the friction and slow down the pendulum. But at low frequencies, the gain here is 1, and at high frequencies, the asymptotic slope is -2. Now, what do you remember about minimum phase systems from some class or another? Where do you talk about Bode plots? What class? 2100? Do you remember for a minimum phase system, a slope of -2, what that implies? Minus 40 dBs per decade. What is the phase shift? Do you remember that? Knock those numbers out of there from someplace. 180 degrees. Phase shift of a resonance, second order resonance system is 90 degrees at resonance, 180 degrees. So it's 90 degree phase shift here, 180 degree phase shift at high frequencies. because we can ignore the phase shift from the motor because it's at such high frequency. The phase shift is going to be dominated by the dynamics of the pendulum, and there will be a phase shift at 180 degrees at high frequencies above the resonance point. What does that mean for the control system? A phase shift of 180 degrees here gets carried through the sensor back to here, and it changes that negative to a positive. Because 180 degrees complex number is -1, right? So it changes that negative to a positive. And now we're no longer subtracting these two at 180 degree phase shift at high frequencies. We're adding them. And the system becomes unstable. A small error makes a bigger error, which makes a bigger error, which makes a bigger error, until the system is going from positive saturation to negative saturation forever. So, rule of thumb is don't let the system get near 180 degrees. Cap it at around minus 135 degrees or so. And to do that, if we have a negative phase shift here, what are we going to do? Give up. Limit the bandwidth. If you limit the bandwidth to where the phase shift is small, it means that the system is not very fast. Then you put a step function in, and slowly the angle changes up to where you want it to be. That's unacceptable. We want the system to be fast. So to do that, we have to cut down the phase shift at high frequencies, but not add too much phase shift at low frequencies. And so what we're going to do is build a compensator. Looks like this. Log F versus log A of the compensator. This is the D part of the PID algorithm. Actually, here's the proportional part. Here's the proportional part. We're going to set some gain, and then at some frequency, we're going to cut over and make the slope here +1 on the log-log plot. +1 on a log-log plot. Does anybody remember what that maps to? If you have a +1 in S space, or in J omega space, that corresponds to what in the time domain? That's a fairly obscure question. It's a differentiator. Why? Because when you differentiate cosine omega t, if you differentiate that, the lead term is omega. Take the log of omega, you get +1. So we're going to add a derivative term above some critical frequency. What critical frequency? It's about the time constant of the motor. Of the pendulum. So, there's going to be a proportional term here. Bigger is better. Bigger is more accurate. Bigger is more accurate, but can cause oscillation. This will help suppress oscillation. Because it reduces the phase shift at high frequency, and therefore gets the system away from minus 180 degrees. So let's zero in on the PID algorithm then. And I'm just going to write this out, and then we'll go through it in more gory detail. So the PID function that we're going to use is going to be P times the error at time n plus D times the derivative of the error. So that would be the error at time n minus the error at time n minus x, where you get to choose x, plus some integral term. No, we're not going to do it that way. We're going to do it this way. We're going to say plus the min of some I max times a constant I plus the sum over some range I'll talk about in a minute of error n times dt, but we're going to cleverly set dt to 1. So the range of integration is going to be from last zero crossing of the sign of the error. Oh, okay. So the bottom boundary here is set to 0 when sign error is not equal to sign error minus error n minus 1 n. And we're going to go from this time up to the current time to n. So a derivative is you take subtract errors. Integral is you add them all together.
When you have the equal sign there, are you talking, what is that?
What equal sign? This one?
Yeah.
That's n,
Oh, okay.
as in that one. Okay. So you're going to add together the last few samples from the time that the sign of the error changed until the current time, scale it by some integral term, and probably bound it to some I max, because integrals by their nature have a tendency to grow without bound, unless you reset them or control their value some way. So again, higher is better here. It's going to minimize the error, the total error. But you're going to have a derivative term to compensate the phase shift of the pendulum so that the high gain here does not cause oscillation. So this term is going to compensate the proportional term at high gain. And the integral And for example, in the units I chose for this simulation, P had a value around 200, D had a value around 16,000, and I had an amplitude of about 1/16. So the integral term is small in terms of the total contribution. The integral term, because it is a negative phase shift, will destabilize the system just like a high gain here. So you want to not destabilize the system too much, but you want, if there's a static error, let's say this is the desired value, system comes up, overshoots, you want it not to stay at a low level forever, just below just below the desired value, you want to slowly creep up as the integral term gets bigger and bigger. And just creep up towards the final desired value. So you want this term to be the creep up to the final position term. So, high gain, highest possible. So how would you tune this? Set all of them to 0. Set all of them to 0. Turn up the proportional until it starts to fly. Turn it up a little more. And you will find that as soon as you apply the power, the thing tries to go around, around, around. In other words, it's not compensated correctly. So as soon as you start to get unstable behavior, then you add a little bit of D. And you creep up on this by increasing P and D until you get a fast, stable response. Which is why it took me a week to do this, first time. Turns out this particular response is not the most stable. But the MATLAB is pretty closely tuned to optimal. I was playing with KI this morning. KI 1/16 is stable, 1/2 is stable, 0.75 is unstable. That's a small value compared to 16,000, but remember this is differencing and this is summing, so it's hard to scale them all. You're going to have to get these two correct, get it fast, and then if there's a bias towards underperforming here, towards being a little bit too low below the desired, add in a little bit of integral term. This suggests that after the first thing you do, which is get the DAX running, the next thing you're going to do is get the user interface running. So you can change these quickly and not have to recompile every time you change the values. Get the DAX running, get the user interface running, then tune it. Even though tuning is the central piece of this, of your grading, do it last. Do it soon, but do it last, because you need the other two in place for efficiently tuning. So, questions. There's a lot here. The bottom line is a fairly simple equation you're going to have to program up fairly fast because it needs to run 1,000 times a second. You're going to do all these estimates 1,000 times a second. Oh, by the way, because the sensor is noisy and because taking derivatives amplifies the error relative to the value, I chose X to be 4. I actually compared samples that were 4 samples apart rather than adjacent samples because that gave a little bit bigger difference, and so the difference tended to be bigger, tended to outweigh the noise. You could, however, do a better estimate of the first derivative. How many people, have anybody ever heard of the Hilbert approximation to the first derivative? I hadn't either until I read MATLAB documentation. You could fit a straight line. You could measure 4 errors in a row, fit a straight line, and use the slope of that as the first derivative. You could fit a cubic spline to it and take the first derivative of the cubic spline. But at least you're going to have to worry about noise control in this term. think this over and come back with questions for Wednesday. I will have the lab open tomorrow morning if you wish. First, on first request, of course. Yes?
I had a question for one of the earlier equations you had where it was like out in terms of like, or as a function of F, you had like C, M, and D.
Mhm.
What was the C in that again? Like M was motor and
Controller. It's the controller. It's the PID term.
Okay.
Yeah. Okay.